Okay, so now let's prove that some of these are actually covering spaces. Let's say this one, given by span, is a covering space. So according to the definition, we should select an element in the base. That's a one-dimensional subvector space of R3. So let that be an element of RP2. Next, we're supposed to show that there exists an open neighborhood about that, so that the preimage, or so that the preimage of that open is homeomorphic to that open cross some set. Now, to think about what that set would be, let's just think about straight up what is the preimage of this element to begin with. So note that in this case, span inverse of this element V is, well, it's all the unit vectors whose span is the one-dimensional vector space V. And I can write this in two ways. One is, this is a fancy way of writing it, it's the set of orthonormal bases for this one-dimensional vector space V. But being one-dimensional, that's just to say that it's the set of unit vectors in V. So alternatively, this is simply the vector space V intersected with the two-sphere. It has two elements in it. So the problem then of showing that this is a covering space, in some sense, can be phrased as the following. If you're given a choice of a orthonormal basis for V and a nearby one-dimensional vector space, nearby in the sense of the topology on RP2, is it possible to determine an orthonormal basis for that nearby one-dimensional vector space as well, from this choice of one for V? And furthermore, is it possible to make that choice continuously, at least continuously among neighbors, close enough neighbors of V? So that's the problem we're facing in showing that span is a covering space. So to satisfy the definition of covering space, we should produce an open neighborhood of RP2 about this. So here's one. Consider, so take U to be the set of all other one-dimensional subvector spaces that are sort of close to V. So maybe those that when you project them, orthogonally project them onto V, it's an isomorphism. That will be useful so that then if you choose a basis for V, you can just look at the inverse of that isomorphism on that basis to find a basis for this W. So I'll write that out such that this composite, which I'll write as alpha sub W, it's a map from a linear map from W, including into R3, followed by orthogonal projection onto V, such that that linear map is an isomorphism. So that's evidently a subset of RP2. Now I'm just going to leave it to you to check that U in RP2 is open. Know that to check that is to use the only topology there is on RP2, which is the quotient topology from this map. So to check that assertion is to check that the preimage of U inside of S2 is an open subset. And you can write down explicitly what that preimage is. it's the complement of the orthogonal complement of V intersect the two-sphere. And note that that's open in the two-sphere. Okay, so we'll give ourselves that this is an open subset of RP2. Note that it certainly contains V, because if you include V into R3 and orthogonally project onto V, that's an isomorphism. It's the identity map. Let's take the set, take the set F to be that set of our all orthonormal bases for V. Take it to be span inverse of V, which you could alternatively write in this way. Now the hard part is to produce this homeomorphism phi between F cross U and span inverse of U, and not any old one, but one such that this commutes. So what will we take phi to be? Well, it'll evaluate on a V, comma, an element of U, which is a W. So V is an element of here. It's a unit vector inside of capital V. And it'll carry it to, well, the unit vector inside of V is an element here. This alpha sub W, which is this composite, is an isomorphism. So you can look at the inverse of that isomorphism, apply to little v to obtain an element of W. The result will be a vector inside of W. It might not be so the span inverse is some subset of the two-sphere. This might not be a unit vector. It'll certainly be non-zero. So just normal scale by its 1 over its norm. So just normalize it. I hope. Who knows if you can see that? It's a vector. I just scaled by a real number, which is 1 over the magnitude of that non-zero vector, thereby producing a unit vector. And this is, scaling is certainly a continuous operation. Taking inverses certainly is. And this all depends continuously on W, just because the projection formula is continuous. So take that to be phi. Why is it a homeomorphism? Oh, first note that if you apply phi and then span, that will be the same as just projecting off of the F coordinate. Indeed, this arrow, this projection, evaluates as capital W, whereas this produces some vector, unit vector in capital W, and then the span of it is just capital W. So indeed, this commutes. And the inverse phi inverse is given by sending a unit vector whose span projects isomorphically onto V to which elements of that product? Well, so it goes to span W, as it would have to, in order for this diagram to commute. And so the real question is, what is this coordinate? Well, that's just that's just alpha sub W applied to V, but then scaled unit length scaled by the norm of alpha v w. Phi inverse is also continuous, and you can check that it actually is the inverse of phi. So that shows that phi is a homeomorphism. So this finishes the proof that the two-sphere mapping RP2 by span is a covering space.